Okay, well, good morning, Year 11. Just as promised, I'm putting up this little video for you to quickly follow up on one of the problems that we presented during the live stream meeting yesterday, which Katarina joined with me. Thank you very much for doing that, Kat. Okay, so the problem I presented up for you to solve was about conservation of momentum. Remember, there's a couple of different types of collisions. We talked about elastic and inelastic of two objects colliding, so usually carts or vehicles. But this one's actually an explosion. So an explosion, where there's an explosive force, like in a gun or in this case a cannon, is also a situation where conservation of momentum happens. Just running over our rules down here, remember our rules are that momentum is mass times velocity, and also that momentum is always conserved, no matter what. And that doesn't matter what sort of explosion or collision it is, or how messy. It doesn't matter. This is a law which is tied to the conservation of energy, and so it will always be conserved. Okay, so let's have a look. If I move this up a little bit for you, we have the cannonball. We already know the mass. It's pretty heavy, 3.5 tons, and a 28 kilo cannonball. It fires, and as you'd expect, once there's the chemicals are lit, the explosion, gunpowder happens behind the ball. Cannon recoils backwards, so has a backwards lurch, and then the ball fires out, well, forwards, obviously. Not much of a cannon if it's not firing forwards. You got the velocity of the cannon recoiling, but not the velocity of the ball. So that's what you've been asked to find in part A. What's the velocity of the cannonball? Okay, so laying out all our data down here, you can see, if I move that up a little bit and blow that up, you can see next to the illustration of the cannon, we've drawn a little diagram. There's the cannon and the ball. Notice that over here we've got the momentum being represented in terms of arrows over here. Okay, so I've got this one here and this one here. So each of these free body diagrams are representing one for the motion of the ball, and everything that's to do with the ball we're going to label B. So mass is mb, velocity of the ball is vb, and momentum of the ball is pb. Same for the cannon, although obviously you know that it's being sent in the opposite direction, so a recoil, and that's a consequence of Newton's third law. Remember, we have a massive lurch forwards, we've got an explosive velocity of a ball going forwards, the equal and opposite force acting backwards, like the third law says, is the cannon. Like it lurches, it physically moves backwards, and it does that with a velocity, I think we said of 5.25. Yes, there it is. Notice in here with the cannon velocity, I have a negative sign, negative 5.25. That's important because velocity is a vector, so is momentum. So you've got to express one of them as negative, one as positive. We've chosen the cannon to be minus and the ball direction to be positive. Got to stick with that throughout. Okay, so let's have a bit of a look. First of all, a helpful thing to do is to quickly sum up what do we know about the momentum. We know that the momentum throughout is going to be conserved, right? So event 1 is just before the cannon explodes, right? So I've got that noted down for you right there on the screen, just before the explosion, and notice that P1 is equal to 0. Okay, momentum is 0. P is momentum, don't forget that. Event 2, just after the explosion, so like the second after everything's gone into motion, well, P2 is actually equal to the momentum of the cannonball after it's been launched, plus the momentum of, sorry, that's the cannon, momentum of the cannon lurching backwards, and the momentum of the cannonball, which has been launched and flying through the air. Now, conservation of momentum should tell you what should the momentum of cannon and momentum of ball total up as. The momentum afterwards, it's always conserved, right? So if the initial momentum is 0, the final momentum should also equal 0, right? Momentum before is equal to momentum after. So you've got to make sure you follow those rules. Okay, so we've got ourselves the momentum mapped out. how would we go about this? Well, we know we've got our equation, right? We have all the variables that we need. We know that the momentum of the first object mass of the first object beforehand times its velocity on leaving plus the mass of the second object, which is the ball, times its velocity leaving is equal to the initial momentum total. Not independently, individually, but the total on this left side is going to be equal to the sum of the initial momentum, which was m1u1 plus m2u2, just using the initial velocities. And it's very handy for us in this little problem because neither of them were moving initially. It's a zero momentum. So we're going to put that into an equation. Well, what equation would you use? Here's the worked one for you to see. I'll just put it up here and make it a little bit larger. Okay, there we go. So hopefully what you can see there is that if I've got the equation where those momenta are added together and equal zero, you can just change the subject of that, right? So if PB plus PC is equal to zero, then PB is equal to negative PC, to subtract the momentum of cannon from the left side and get it on the other side. And then look at this neat little formulation. I've got momentum is equal to the negative momentum of the other. Momentum of ball equal to negative momentum. All right, use your equations for momentum. You know what to do. MBVB is equal to negative MCVC. Negative because remember its velocity is in the opposite direction to the cannon. Got to pick one. So, well, actually we've made cannon negative, ball positive. Doesn't matter which way you do it. All right, so change the subject of this equation. Divide both sides by mass of the ball, and I've got MCVC divide by the mass of the ball, and just substitute your values in here and here. Put them in. We know the mass of the cannonball, 28.5. It's already in kilograms, no conversion needed. And when you put all that into a calculator, there you go. So that is the velocity of the ball. Velocity of the cannonball. 672, which you'd expect. Very fast. It's lighter than the overall scenario. The cannon is heavier. Remember the gigantic cast iron cannon, firing pins and a huge cart that it's attached to. It's heavier, so its recoiling velocity was smaller, 5.25. Do you see that up here? 5.25. Compare that to 672. It makes sense. Lighter object is going to travel further, faster, because momentum's conserved and its mass velocity ratio is going to be lower on mass, therefore much higher on velocity. Okay, so let's move that up a little bit. What's the source of the kinetic energy that's now? Oh, sorry, no, that's the next part. Hang on a moment. Part B, the kinetic energy of the cannon and the cannonball. Let's go over here for that. So just using straight equations over here. So I've got it for you there. Part B. And it's here solved for you. Remember kinetic energy from the last subtopic, you know the equation, half times mass times velocity squared. And look, you've got to calculate it separately for each of the cannon and the ball. So EK means kinetic energy of C, cannon. So half mass cannon velocity squared, and just substitute your values in straight up, and there they are, kinetic energies, right? So there they are. Sorry, just annotate that for you. Here and here. Okay, so interesting. You've got the cannonball kinetic energy is higher by by about 100 times, right? And that is the 10 to the 6 compared to the 10 to the 4. And we'd expect that to be the case. Kinetic energy is not conserved here, right? Before and after. It's not, it's, right? So this is an inelastic collision. You've done that section, so that's kinetic energy. And last question is a good thoughtful one for you. What's the source of the kinetic energy that's now been translated to the cannon and the ball? In other words, it started with no velocity, there was no motion, but we had an explosive effect in the middle. This is the same effect as like winding up a spring or compressing a spring and clamping it off. If you put objects next to that spring, what's going to happen when you take the clamp off and that spring goes and comes rocketing out? Well, you know what's going to happen. It's going to shoot outwards and push objects on either side out of it. Well, explosions are exactly the same, but what's the difference? Well, the difference is this. In terms of an explosion with a cannon, the source of the kinetic energy is actually the chemicals in the gunpowder. So we've got sulfur and ammonium nitrate and a bunch of other chemicals that have got bonds between them, and they happen to be chemicals that when you break the bonds, you combust them, they release a hell of a lot of, well, it's chemical potential energy. So we'll state that in our answer. Got to link it to energy, so your answer should say energy somewhere. So chemicals in the gunpowder contained chemical potential energy. And that would get you through. If this was the 3-mark question, that would be your 3rd mark right there. And you could say, little arrow, converted to kinetic energy. Okay, so that's it, guys. That's our total solution for this. Remember, this whiteboard is accessible. You can follow the link to this now. It's been updated. So that whiteboard, you can follow the link to that in Teams in the week 4 channel. I put a link up there. If you click the link, you go to the live shared whiteboard here online. I'll also put up a little picture of this as well. Okay, guys. Leave you with it. Hopefully you were successful and attempted that first, but if you didn't attempt it before you saw this solution, work through the steps and make sure you know. Visualize things first, use the relevant equation and substitute the known values in, but do it carefully. See you later.